Now let me go back to the slides and then talk about that little exercise that we can make sure that we really understand hierarchical model. And in this case, I want just to throw out the possibility of having a schedule specific mu j and also a schedule specific sigma j. And so we, so far for this whole lecture, we've been working with the case that we do have group specific mu j, but we only have a shared sigma just to make the model a little bit easier to deal with. Okay, but if you remember, before we do that simplification, there was this argument that, well, in the data, the standard deviation doesn't seem to be very similar across the different groups. Okay, so making that assumption is probably not a good idea. So now let's relax that assumption a little bit. So instead of doing mu j as a sigma j as a shared parameter, we're going to have a sigma j that is going to be schedule specific. Okay, so let's look at how the model can be set up. Okay. The model in this case is going to be equation 29. So we're going to have a group specific mu j and a group specific sigma j. We're still going to have nj as the number of observations in group j. Okay, so you could imagine that this, other than the sigma j part, everything is exactly the same as the previous model that we have fit. Okay. All right, so that's the starting point. And then, like what we talked about, probably not a suitable, a more suitable hierarchical model than before, because the data does tell us quite different standard deviations in the sample. So using a group specific sigma j is probably better than using a shared sigma. Okay, so that was the motivation itself. And then the rest is, well, now we have this different model. We have more than one sigma that we need to give priors to. Okay. Now we could choose to do a two-stage hierarchical prior again for sigma j. So we're able to borrow information across different groups to utilize the structure of doing hierarchical modeling. So with that, let's first of all recall that, well, for mu j, we have been given this normal mu tau previously. And now if we want to do something about sigma j, if we want to actually also utilize the conjugate result that we had before, we could technically give 1 over sigma j squared, all of them to follow the same gamma distribution. So I will use, I don't know, SA and SB. S stands for sigma in this case. So if I want to specify a shared gamma prior, which is the first stage prior for sigma, then we will be able to have conjugate result over here. So before we move on, equation 31, which is what we done before, and let's just suppose this is equation 32 for now. What do these two prior mean in the context? We talked about 31 extensively previously. What does it mean to have all of the mu j's having the same prior? And now we're adding 1 over sigma j to the pool as well. So let's spend about 2 minutes with your neighbors to make sure that we know why do we want to do this in first place. And later on, we're going to discuss how the coding and everything can be done accordingly. Okay, so pause here. All right, it's definitely being very quiet today. So maybe let's talk about equation 31 first, and then give you the chance to talk about 32 next. So 31, as we know, is we are using a shared, look at the note, shared normal prior for all of the mu j's, okay? And we're using the conjugacy result that we have from before. So because the data follows the normal model and mu j is the mean, so we are giving a shared normal, which is conjugate in this case, so that we can work with like easier formatted posterior later, even though we use JAX, but nevertheless, this can help us on making sure that it's staying on track and everything. So mu j, when we are saying that each of the mu j is coming from the same normal distribution, and we know that the normal has mean mu and standard deviation tau. What we are saying is that we think the mu j's are related to each other. Okay, they're not the same, but at the very least, we think the mu j's are related to each other. Moreover, we think that all of them are coming from the same normal distribution. Okay, so we're saying that on average, each of the mu j is going to be equal to mu. Okay, that's what this normal model is saying for equation 31. And also this tau, if you remember, so tau is the standard deviation of this normal prior. If tau is very large, then you're probably suggesting that the mu j is going to be quite different from each other, even though they're related. Okay. But if tau is small, then that is indicating a smaller spread of this normal prior. So what that means is that you think the mu j, even though they're related, they are related to each other, and they probably are pretty similar to each other as well. So if you just focus on equation 31 itself, even without thinking about, oh, I don't need to worry about if it's a hierarchical model or anything. If you just look at this itself, what this is saying is that mu j, all of them comes from the same prior. The mean is mu, tau is the standard deviation is tau. So what this is saying is that the mu j's are related to each other. They all share, or they all should be somewhat around mu, and tau is going to control how mu j is going to be different from mu or different from each other. Okay. So that's what equation 31 is about. Okay, and that's what we did before. So this mu 32, let's just say, we're saying that if we now, in addition, specify a shared gamma prior for all of the sigma, which will be 1 over sigma squared, follows a gamma distribution with hyperparameter SA and SP. So what do you think this prior mean for this 1 over sigma j squared if we follow the same logic about equation 31? Okay, so let me pause here one more time and put people in the breakout room one more time as well. So this is slide 37, and give you the chance to maybe reflect what we did in 31, and then to think through what we were trying to say in 32 itself. And then we're going to proceed about the mechanisms of the computing and all that. All right, so for based on the discussion that we had just now in small group, I think we can probably say that, well, all of the sigma j's are related somehow if we have equation 32, okay? And specifically, there was a question earlier about what will be the mean and standard deviation of the gamma. Well, I never always remember whatever the form is, but I think the mean is going to be SA over SP. And then the standard deviation or the variance, I guess, is SA squared over SP squared. So that will be one way you can tune, you know. If you say,
Professor, it's SA over SP squared.
Thanks. Okay, so let me write it down. The mean for gamma is SA over SP, and then the variance is going to be SA over SP squared. But of course, this you can always look up. I always do that when I don't remember something. But I think the lesson over here is that in equation 31, because we know that mu and tau, they're the mean and standard deviation, so it's kind of straightforward to think about how to tune them, right? When you're trying to decide whether mu j's are very similar to each other or not very similar to each other. When you're having a gamma, like in 32, is less straightforward. But we know that the mean for a gamma SASP is going to be SA over SP, and then the variance is going to be SA over SP squared. So you can choose accordingly this SA and SP to reflect your prior belief about how the sigma j is going to be similar to each other. Okay, so just like what we were talking about in equation 31 for the mu j's, if I think all of, so first of all, 1 over sigma j squared itself, I can tune my SA over SP to represent on average, I think, how they should be, okay, because that's the mean of this gamma. But then if I think all of the sigma j's are quite different from each other, then I can probably have a roughly larger SA over SP squared, because that's the variance of this gamma distribution, okay? If I think they are quite similar to each other, not very far away, then I can give a prior distribution that is showing a smaller variance. Okay, so this is getting into maybe some of you are curious about, you know, very early on as well as how you can choose a prior appropriately, because we know the prior should reflect what we believe before we see the data. Okay, so when we're covering this hierarchical model concept over here, there are even more subtlety that we can deal with. For example, even though we might not give the values of mu, tau, or SASB, but we know that their relationship can tell us certain things about how we believe of this mu j among all of the mu j's and among all of the sigma j's. All right, so keep that in mind, and we can go to the next part over here. So if you remember, this is what we had before. If we have a shared sigma, this is the hierarchical model graphical representation that we had before. And now I would like you to actually update this graphical representation to reflect that we not only have a shared sigma, but a, do I have it over here? Okay. I don't have, yeah, I don't have it, but we can work on this one directly making updates. So the question or the discussion question for you all right now is how can I update this graphical representation if instead of sigma, I have sigma j? So take a moment to work through, and then we're gonna look at it together. And I think this will enhance your understanding about the different stage of the priors that we're specifying over here. All right, anyone wants to offer what you think that the update we should make over here to make it as a, instead of shared sigma, we're gonna have sigma j for each of the group. Which part of the graphical representation I should update and how? Yeah, Carl?
So at the top, you can have new tau SA and S. And
Okay,
then the new tau still points to mu one dot 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 mu j.
Yeah.
Whereas the SA and SB points to sigma one dot 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 sigma j.
oh, I see. So I guess first of all, so let me, okay, use a different color. So maybe I will cross out this part, right? And then I guess what you were saying is instead of sigma, this color. So instead of sigma, I'm gonna have a sigma one, right, for the group one. And then for sigma, for group J, I'm gonna have sigma J. And then you're saying that we can direct the hyperparameters over here, SA and SB. So maybe alternatively, we can maybe move them all down and then doing the arrows from bottom up. That probably will make things a little bit easier to work with. So following the idea that Carl suggested, we can have something like this. Okay, so I crossed out the existing sigma part with the two arrows using the blue color, and then I use the regular red color over here to make the update. So you could, of course, put everything on the top, but just harder to point and all that. Since for our model, if we start to have sigma j over here, then we know that, well, we have a bunch of parameters over here about the mu j, so we can use the top part to represent the mu j's, and then we have the arrows one more time pointing from the parameter to the data, and then from the hyperparameters to the parameters themselves. And then at the bottom part, we can utilize that section for representing the sigmas. So instead of a shared sigma, we don't have a shared sigma anymore. We have each of the sigma for a particular group, and then it's going to be group specific. So we have sigma one pointing yi1, that's group one, and then sigma j to yij, that's group j. And then at the end of the day, we also have the hyperparameters that we're having pointing to the parameters themselves. So in the past, we only have the top part because we don't have a group specific or schedule specific sigma j. So everything is a little bit simpler. But of course, if we do believe that we should have a hierarchical prior for the sigmas as well, then this is the way that you can update the graphical representation, which is reflecting what we had written out earlier about the model itself. Okay. All right, then of course, once you do that, we will have the two-stage prior for mu j and two-stage prior for sigma j that we have talked about before. So hopefully the rest you can fill it out later on as you see all of the different details, but I just want to use the time in class to talk through what are the model assumptions as we specify equation 32 now, and then how we can give the prior accordingly. And the graphical representation that we showed earlier overall gives you a visual of what we are doing actually when you're trying to figure out different pieces. Okay, so this is the previous code, as we know. So if you remember, we have the chunk for doing the likelihood. Okay, so this probably wouldn't change much, but of course, this probably will change now because earlier we have the inverse sigma 2, which is the inverse sigma squared itself, is being shared. Right now, this should be also indexed by j, because we're gonna have a vector of inverse sigma j as well. So you're gonna have, so I'm just gonna try to use my my pen over here to highlight the changes that you have to make. So here, this should be j specific as well. Okay, and here you should probably add a line about inverse sigma 2, also j. Okay, and then they all should be a gamma. So you have to add another line in the prior section as well, because now in addition to mu j, we also have the inverse sigma squared to be following its own gamma accordingly as well. Okay, so this should be added over here, okay? And then the rest, I think, is just gonna, so in that case, you probably don't have this one anymore because this will go into the loop, because now you're gonna have a group specific sigma square as well. But then in terms of tau, I think things don't change, mu doesn't change. And then if you want to track each of the sigma j, you can always use this trick of returning them as well. Okay, so if you ever want to fit this model, which seems to be a more suitable model for our data, you should give it a try using the relevant R and JAX code in particular, and then do the updates. And then you can see what the result's gonna be looking like compared to before. And that will be a good practice to make sure that you know, first of all, how to fit a different hierarchical model, and then how to write JAX to fit to estimate the model itself. And lastly, how you can compare the results between the two models. All right, so to recap, we have once more 3 general steps. Okay, you have your prior, you have your sample, and then you use Bayes rule to update the previous opinion. And that's where you go to the posterior. And then for the particular case, when we have continuous outcome in groups, we are considering a hierarchical normal model. Specifically, we did a 2-stage prior for mu, but it's possible to do a 2-stage prior for sigma if that's what we want to do, which is the little exercise that we did together. And then specifically, we use JAX for MCMC. So you need to make sure that you know how to write JAX code, how to make your own, and then how to perform MCMC diagnostics, and then make changes accordingly. We also talked about shrinkage and pooling effects and source of variability that was from last week. So those are the important recap highlights from this lecture. Any questions about the code, about the material for this chapter? Because this will be the final part about this hierarchical modeling. And then starting from Friday, we're gonna start the last topic on Bayesian regression, which I think some of you will be using that for your project. So it will be useful to introduce that as soon as we can. So we're gonna do that first and then do the case studies.
Can we go back to the code?
Yeah.
Sorry, just how do we edit that, the inverse sigma 2 line? We're putting that in the loop, and then how are we changing it?
Yeah, good question. So, well, I don't usually remember exactly the syntax, but I'm suggesting you adding it right after the line of the mu j. And roughly, I think the code will look like something as inverse sigma 2. And we're actually treating it as a vector once again, because we have sigma j, right? Sigma 1 to sigma capital J. So I think you're adding a line like this. So I think it's going to be a d gamma. And then I guess we will have certain names. I don't know, let's just say I use SA, right? And SB. So this will be what you should add within the loop over here, but immediately after the mu j line. And another thing you need to change over here is that instead of the shared inverse sigma 2, here you should be having inverse
Sigma 2j, right?
Yeah, and also using the schedule I to make sure that you get the right j. If that makes sense.
Yeah.
Yeah. So I think that would be the main thing. Let me just write it out. So that would be the main thing that I think you need to change. But accordingly, because now we're introducing, as you can see here, SA and SB as well. So you will need to add them into the hyper prior sections to give them the appropriate hyper priors as well, if that makes sense. So I think you don't need this anymore. This will go into the loop. But the way that you write the loop will be very specific. And this, again, JAX code itself is supposed to be very descriptive of the model that you're fitting. So I think it's always good to write it out what the model should be looking like. And then you can compare back and forth to see if your JAX code is really descriptive of the model, because that's always a good way to debug whether you have done any mistakes in the coding itself.
Great, thank you.
Always. Anything else? Okay, all right. So if not, I'm gonna just stop share, and then I'll stop the recording here as well.